Okay, so we're going to kind of continue on with what we talked about yesterday. At the very end of class yesterday, we talked about what a transformation is and what makes something a transformation in geometry. Can anyone remind me what we said yesterday about what makes something a transformation?
The number of points either stays the same or gets less in the image.
Okay, so that would be if it was a mapping. But what did we say has to happen in order for it to be a transformation? You're on the right track. Parker?
They have to have the same amount of points.
They have to have the same amount of points. Very good. Okay. So we talked first yesterday about like what makes something a function. We looked at the arrows and being able to understand like what we saw in our bell ringer today. If it has more than one arrow coming off of a point in your domain, then it's an automatic no. Okay. And then we took that and we went into mappings. Mappings is when you had to have the same amount of points or you had to start with more points than the shape that you were going to. And then we got really specific, and with transformations, we said they have to have the same number of points in both shapes in order for it to be a transformation. It's the same idea as when we said we have one-to-one functions. That's when everything from the domain had one specific location, nobody was going to the same spot in the range. So we're going to talk about specific types of transformations. And in the next, coming days, and even in the next unit, we're going to spend a lot of time talking about these transformations. I've talked about transformations a little bit before. I said that eventually we're going to start talking about the specific types. Okay, and so that's what we're going to get into today. But there's something called an isometric transformation. Okay, so we're adding another word here. Another way to say this would be if it's rigid motion. And that means that you're going to keep, bless you, or you're going to preserve same shape and size. So a transformation meant that you had the same number of points in both shapes. Isometric transformation means we're being a little bit more specific now. The shapes are going to be the same and they're going to be the same size. So they're not going to get bigger or smaller. They're not going to change the way that the shape looks. We're going to keep a triangle and keep the same triangle when we kind of do our transformations here. There's three types of isometric transformations. There's something called a rotation, a translation, and a reflection. Okay, we're going to kind of dive into each of these individually. So let's focus on the rotations first. Think of a time when something has maybe rotated. What does that mean to you guys? What does a rotation mean? Keegan?
Like it's the same thing, but it stays the same way, just like changes like the direction it's facing or in.
Okay, Kendra, is he doing this? Circle? What it like turning? JD?
Yeah, like what they're saying.
Like you turn the shape?
Yeah, like you have the shape facing one direction, and then you just turn it like to a different way.
Yeah, so think about like if you're driving a car, riding a bike, a scooter, a skateboard, something like that have wheels on it. If you're riding your bike, are your wheels like getting bigger or smaller as you ride your bike? No. Okay. Are they like changing position on the bike? Like are they moving or shifting in between your bike or anything like that? No. Okay. They're staying the same. They're not changing as far as like how the shape is being affected. But as that bike goes or as your car goes, your wheels go in a circle. Okay. They start to rotate. So another word you can use for rotations is a turn. If you can turn the shape, you can do a rotation. That's basically what that means. So if I look at these two here, these two shapes I have, the one here on the left, kind of this bluish one, that's my pre-image. And then the one over here in gray with all those prime markings, that's my image. So if I compared those, it looks like they stayed the same shape because they have kind of the same formation. And it looks like they didn't get any bigger or smaller than each other. They look like they're the same size. However, it does look like the one on the left was maybe turned in order to now face this direction a little bit. So I'm going to go ahead and say that yes, a rotation is isometric because a rotation would not change the size, would not change the shape. It's just going to change the way the shape is sitting on your coordinate plane or on your space in your paper or something like that. Okay, the second type of an isometric transformation is called a translation. So look at these two triangles that I have up here. This one's different than the rotation. It doesn't look like the triangle got turned at all. Would you guys agree with me? They're kind of staying in the same position. What it looks like happened is maybe they just took that shape and they pushed it. Okay, so another word for a translation is when you slide something. When you do a translation and you're sliding it, you could move it to the left, you could move it to the right, you could move it up, you could move it down. You could really do any combination of those things. So like this one looks like maybe if I just pushed it over to the right that they would match up, but they could have also said, you know what, I'm going to push it to the right and I'm going to push it down on my graph. Both of those things would be a translation because it's not changing the overall orientation of my shape. My shape is kind of staying in the same position. Again, would you guys agree that those triangles look like they're the same triangle, same size?
Yes.
Yeah, so I think translations are also going to be isometric. Okay, and so the third one we have here are called reflections. What do you think of when you think reflection? JD?
An image just flipped up backwards.
Okay, image flipped backwards, Keegan?
It's like, I figured out this one where it was from the calendar, where it's like they're on one side of the phone, and then like you go to the other side, it's just like flipped, but like the same size and shape and stuff.
Okay, good, love it. You guys ever looked in a mirror before? What do you see when you look in the mirror? Hopefully yourself. Okay, so your reflection is in the mirror. If you guys stand really close to the mirror, like if this is my mirror, and I'm standing really close to it, is my reflection going to be really close to the mirror too? Yeah, and if I walk away from the mirror, does my reflection get smaller? Yeah, so it's proportional there as far as that distance from the mirror is. But if I had something written on my shirt like Bulldogs, and I look in the mirror, does it still say Bulldogs? It still has those letters, but what happened to them all? They got flipped backwards, okay? So a reflection, another word for that is flip. And yes, like you said, Keegan, when we think about reflections, we're going to be reflecting over lines. There's going to be something like a straight line that could be in between those two shapes. That's called your line of reflection. For example, on this one, there could be this line right here that just goes like straight down the middle. And it kind of shows that that triangle on the left got flipped over and it's landing there on that triangle on the right now. They look still like they're the same shape, same triangle. It's just everything got flipped backwards now. But you can see kind of what I was talking about. L and L prime, they would be about the same distance away from your line of reflection. And so would M and M prime and K prime. Okay, but did the shapes get any bigger or smaller, guys?
No.
Nope, so it's still isometric. So those three things, reflections, rotations, and translations, are all going to be considered isometric transformations because they don't change the shape and they don't change the size. Now let's talk about what something would be then if it's non-isometric. So non-isometric means that it could possibly change your shape and maybe your size. So it could do both or it could do one of each or just one of the two. So this is going to be it changes shape and or size. So this is basically the exact opposite of what we were just talking about. Now there's two types of non-isometric transformations, okay? Isometric was reflection, rotation, and dilation. Reflection, rotation, and translation. The non-isometric ones are going to be a dilation and a stretch. But we have to be able to understand what the difference is between the two. Okay? Let's start with the dilation. Have any of you been to the eye doctor before and you had to get your eyes dilated? Okay? What does that do? What does it do when you dilate your eye? It changes the size of your pupil. Okay? Now, your eyes automatically do this anyway when we turn off and on lights, okay? Because your pupil is filtering in the amount of light that your eye is taking. So if I were to turn off all the lights, if we were to make the room really, really dark, it's going to make your pupil get bigger because your pupil is trying to find light so you can see what's going on. If I all of a sudden turn on all the lights, your pupil is going to quickly shrink because there's a lot of light happening and it's trying to filter that out, okay? When you go to the eye doctor, they dilate your pupils. What that means is it makes it bigger permanently because what they can do then is see better into your eyes, okay? But it then makes everything really, really bright, and that's why they suggest like to wear sunglasses after you get your eyes dilated. But when you think about a dilation, the entire thing is going to change its size. Like when I get my eyes dilated, not just part of my eye, my pupil is going to change its size. The whole thing is going to change its size. Okay, so dilations, when we look at them like here, we're changing the size of the shape, but it's changing in all directions. So the entire shape is getting bigger or smaller. Think about too, like with photography. You know, if someone takes a picture, like a family picture, and then your mom wants to get it blown up and she wants to hang it up in your house somewhere, she's going to take that image and she's going to go to, you know, a store or something, and she's going to ask for a bigger print, like a 16 by 20 or maybe. Or maybe when you guys got your school pictures taken, someone ordered you to have like an 8 by 10, a 5 by 7, and maybe some wallet-sized ones. You know, when you look at those pictures, they all look the same. It's just they either got smaller or they got bigger, but they were going that way in all directions. So dilations are not isometric because they change the size of your shape. But if you look at that set of triangles, it didn't change the shape at all. I still have two triangles. It's just that my second one got bigger. Okay? Now, the second type is a stretch. Does anyone know the difference between a dilation and a stretch?
Stretch is like only making it bigger because you can't like stretch something the other way because it would just be like making it smaller.
Okay.
It's like pulling the shape in one direction.
Pulling the shape in one direction. Okay. So it's kind of like a dilation in that it is going to affect the size, but it's not going to do it in all directions. So a lot of times when we think about changing the shape here with a stretch, it's going to kind of make the shape look a little goofy. If you guys have ever had to do like a slideshow presentation for a class, okay, and you put in an image on there, if you grab the corner of the shape and you pull on the corner of your picture, what does that do to the whole picture? Makes everything bigger in all the same directions, okay? So that would be a dilation. What happens if you grab your picture and you just stretch it this way on the edges, or you stretch it this way? It looks a little weird, okay, because that's stretching it. So it kind of distorts the image, maybe makes it look a little fuzzy or like pixelated or something like that. So that's kind of the difference I want you to think about here. Now, if you look at these stretches, sometimes they're going to be able to keep the same shape. So like on these triangles, they stretched it like left to right. It's like they grabbed E prime and they grabbed the side in between F and G prime and they like pulled it. Okay, that's the stretch. But there's still two triangles, but it's not isometric. Okay, because again, it changed its size. What happened on the second stretches example? It got stretched, so it changed its size, and did it change shape this time? Because I started with like a square, and then I went to like a rectangle. Okay, so this is not isometric because again, it's changing the overall appearance of the shape. Okay, so let's kind of summarize what we talked about there. We said that a dilation is something when it changes size proportionally. Proportionally means in all directions. And the example I gave was change the size of your picture using the corner. So again, if you pull in an image, or if I do that, if I pull in images on here and I wanted to just do a dilation, I'd grab the corner because that's going to make it go bigger in all directions. That's going to keep it proportional. A stretch changes size in one direction. And so, like I said, that kind of distorts your picture. Makes your image look a little bit weird when we stretch it versus doing a dilation. So what we're going to do now is we're going to look at some examples of this where we're just trying to identify with whether something happened and if it was isometric versus non-isometric. So remember, isometric would mean it doesn't change its shape, it doesn't change its size. Non-isometric means that the shape or the size got changed. And then we're going to also be able to say what happened to it. So down here at the bottom of our page, we have this picture of this little dog. Okay, over there on the far left is the original image. Okay, so that's my pre-image. Now they've done something to this dog 3 different ways. And what we want to do is figure out whatever they did, was it isometric or non-isometric? And then what specifically do we think they did to the dog? So do they think they reflected it, rotated it, stretched it, all that stuff? So if we look at the first one, letter A, does it look like it stayed the same dog?
Yes.
Okay, does it look like it stayed the same size?
No.
No, it got smaller. So we would say this is non-isometric. And I'm going to abbreviate that. I'm going to say non-iso. Now, to be a non-isometric, that means they either dilated it or they stretched it. So what do you think they did to the dog? Why dilate, not stretch?
Because it shrunk it instead of they didn't make it distorted in any way.
Yeah, the dog doesn't look it doesn't look funny to me. When I say funny, it doesn't look like it got wider or like any weird, like directionally. It looks like the whole shape got blown down. Okay, they look like they're the same dog, it's just this one's a lot smaller. So I agree, that would be a dilation. What about B? ISO or non-ISO? Good, still non-ISO. What'd they do this time? Yeah, this time they stretched it. Okay, now the dog looks a little bit more distorted. Okay, if I kind of were to compare, the heights of the dogs look like they're the same. So like from the top of the head to its paws, looks like they're the same size height-wise. But if I were to compare width-wise, the dog got a lot wider. Since it didn't get any taller and it only got wider, that's why it's a dilation, because now it looks a little bit odd. How about C? Isometric or non-isometric? Okay, do we all agree it looks like it stayed the same shape, same size? Yeah, I don't think it got any bigger or smaller, so I'm going to say ISO here. What did they do? Keegan? Rotated it. They took the original dog and they just turned it on its side. They did a rotation there. Good. Okay, so why don't you guys turn your page over? And there's an example just like this with this little baseball guy. I want you guys to do that one on your own here. Give you a couple minutes to fill that out. Okay, for letter A, did you say isometric or non-isometric? And what'd they do?
Rotate.
Good, I agree. B?
ISO.
ISO and reflection. Good. Okay, again, look at how that one's backwards now. He's facing the complete opposite direction, so that's why it's a reflection. How about for C?
Non-ISO. Stretch.
Good. Okay, do we understand how to classify those things, guys? Okay, so now instead of just looking at pictures like this, we could do this as long as we wanted to, but eventually we're going to have to start graphing things because eventually you're going to be expected to do these on your own. Like I'm going to give you points and I'm going to say, hey, perform a rotation of this much or perform a reflection over this line. And we are going to be able to do that on the coordinate plane. So we're going to kind of get started with that today. What they've done here is they've kind of given us a lot to use. Okay, so they're kind of outlining this process for us. But if you look at this picture, we have this triangle already on the graph. Now, in the middle of the chart here, it says pre-image points. So those are the points that make up that triangle. So they're already giving you that information, which is kind of nice, because sometimes they won't. Sometimes they'll just give you the picture on the graph, and you'll have to find the coordinates. But they're kind of helping us out there, and they give those to us. Now, down here, they give us this coordinate rule. We talked about those the other day. when we had coordinate rules. And that's when you start to change the things about your shape. So that's going to start to impact what it looks like. So we'll talk about this here in a second, how to work with that. But we're going to take this coordinate rule, we're going to apply it to these pre-image points, and we're going to get our new coordinates for our image. So you'll notice over here it says A prime, B prime, C prime, next to all these blanks. Then it's going to ask us to answer those questions. Is it isometric or not? And what do they do to the shape? Okay, so let's take a look at the coordinate rule. If we look down here, this is the coordinate that you start with. Okay, so that x, y, that's just your original points. The arrow is telling you this is what's happening to it. Are they doing anything to the x? No, they don't change anything about the x coordinate. Okay, so up here where it says A, B, and C, -1, 0, and 4, those are all your original x's. We're not going to change those at all. So let's just copy those back down over here. So -1, 0, and 4. My x's stay the way they are. What would you guys say looks like is happening to the y?
They become negative.
Okay? I want you to be careful with this thinking. I don't want you to assume that just because there's a negative there that it means everything stays negative. What that negative really means is that you're changing the sign. Okay, so I'm just going to write that underneath it here. You're changing the sign. So if my A coordinate up here for my y is 1, and I change the sign, it would become -1. What happens to the B? And the C?
-1.
Okay, what would happen if it had been -1 instead? Then it would become +1. Okay, and I just want to clarify that because one of the biggest misconceptions I see when they're talking about coordinate rules like this is if they put a negative in front, a lot of times kids see that and they think, oh, everything has to be negative. Negative, 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 okay? But sometimes when you flip the sign, it actually means that you're just changing it to a positive. Because if I had a -4 or a -1, and I put that into a -y, it would switch its sign. Okay, so I just want to clear that up. Now let's graph this new shape. So A prime is at -1, -1. Make sure you label your points too with A prime and all those other labels. B prime is at 0, -4, and C prime is at 4, -1. Okay, so that's what it should look like. Does it appear to be isometric? Same triangle, same size?
Yeah.
Yep, I think so. What does it look like happened?
Reflection.
I agree, reflection. Now, bonus question. What did they reflect over? Good, the x-axis, very good. This is your x-axis right here, guys. So that's technically the line that they use to do your reflection. So in the future, just a little spoiler here for you guys, we're going to talk about specific rules for specific rotations and reflections. This is actually the rule for doing the reflection over the x-axis. You always just change the sign of the y. Okay, so let's do one more. All right, new shape. I mean, it's still a triangle, but it's shifted a little bit on our graph. We've got new pre-image points. My coordinate rule down here, are we doing anything to the x? No. So what should my x points be over here? So 0, 1, and 5. What are we doing to the y's? Yeah, we're taking -2 times all of my y's. So -2 times 0, -2 times 3, and -2 times 0 is still 0. Okay, let's graph this one now. So A and A prime are going to overlap because they're both at 0, 0, and that's okay. B is at 1 and then down -6. That's my B prime. And then C and C prime are also going to overlap. All right, do we think this one's isometric? No, good. What happened?
Stretch.
Why are you guys saying stretch and not dilation?
Because it got pulled and dilation, like made it smaller and bigger, and just like that.
Okay, Keegan?
Because it kept its same shape, you just stretched it down and then if it was dilated, they would have the whole thing really got bigger, but only one side got bigger.
Okay, so like, do you guys see in the middle, A to C and A prime to C prime? It stays the same length. If it had been a dilation, that side would have to get bigger too, but it doesn't. Just like the B point is getting pulled. So I agree, it is a stretch, but I just want you guys to be able to look at a graph and understand that. Because sometimes kids see stretches, but they write down dilation. You got to make sure it changes shapes or changes size in all directions in order for you to say it's a dilation. Do we have any questions about what we've talked about today?